52 years ago, in a quiet corner of northern England, 28 men went to work on a Saturday morning and never came home. There was no war, no earthquake, no act of God, and no act of terrorism. There was only a decision made in a hurry, a pipe that nobody on site truly understood, and a summer afternoon in Lincolnshire that became the largest peacetime explosion ever recorded on British soil. Before that day, almost nobody outside of North Lincolnshire had ever heard of Flixborough, and nobody had any particular reason to. After it, the world of industrial engineering would never think about safety in quite the same way again, and the laws that protect workers and communities from industrial catastrophe across an entire continent would be rewritten from the ground up. To understand what happened at Flixborough, you first have to understand what Flixborough was. And the answer, before June of 1974, was almost nothing. A village of around 500 people, sitting quietly on the floodplain of the River Trent in North Lincolnshire. The kind of place that does not appear on any national map of significance, that people from nearby towns would struggle to locate, that the Encyclopedia Britannica did not even see fit to mention. A flat, gray-green landscape of farmland and waterways, with the industrial silhouette of a Normanby Park steelworks rising in the distance. That steelworks is important because it is why the plant was there at all. Since the late 1930s, a chemical facility had operated on the edge of this village, quietly producing fertilizers using gas drawn from the coke ovens of the steelworks next door. For decades, it was simply part of the landscape. Workers cycled to their shifts. The village lived alongside the faint chemical smell that occasionally drifted through on certain winds. Nobody thought very much about it. In a photograph taken just before the disaster, a young woman can be seen walking her dog along the road that overlooked the plant. She is relaxed. It is a perfectly ordinary Tuesday. That photograph would become one of the most powerful images at the disaster's memorial exhibition 50 years later, precisely because of how unremarkable it is. In the 1960s, everything about the plant changed. The global demand for synthetic materials was exploding. The post-war economic boom had created an appetite for nylon that European manufacturers were scrambling to satisfy. Nylon was everywhere, in clothing, in carpets, in ropes, in industrial belts, in the wiring of electrical equipment. And to make nylon, you need a chemical called caprolactam. It is the raw material, the essential building block without which the whole process cannot begin. A decision was made to transform the Flixborough site entirely. The fertilizer operation was wound down, and a new company took ownership. Nypro UK, a joint venture between Dutch state mines, one of the largest chemical corporations in Europe, and the British National Coal Board. The plant was rebuilt to manufacture caprolactam on an industrial scale. It was commissioned in 1967, and almost immediately it began to struggle to reach its production targets. The facility was designed to produce 70,000 tons of caprolactam per year. By early 1974, it was producing less than 50,000. That gap represented a growing financial wound. The production process itself was not simple. By 1972, the plant had adopted a new method developed by Dutch state mines in which a colorless, highly flammable liquid called cyclohexane was heated to around 155 degrees Celsius and pushed through a cascade of 6 large steel reactors under significant pressure. Each reactor was connected to the next by expansion joints called bellows, designed to absorb the thermal movement of the pipes as they heated and cooled. The cyclohexane was partially oxidized by compressed air as it moved through the system, eventually becoming the chemical compounds needed to produce caprolactam. It was a demanding, high-stakes process, running at high temperature and high pressure simultaneously, with a liquid that at atmospheric conditions would boil instantly and become a highly flammable vapor. At the start of 1974, the plant was under enormous pressure from multiple directions at once. The British government had refused the company's request to raise the price of caprolactam, which meant the plant was operating at a financial loss with no relief in sight. A minor strike the previous autumn had forced the government to restrict industrial electricity use to 3 days per week, and the plant had kept itself running by switching to its own backup generators rather than shut down. And then, in the first weeks of the year, the plant's mechanical engineer handed in his resignation and left. No replacement was found. By the time disaster struck, months later, no one at the facility held a professional qualification in mechanical engineering. That absence would prove decisive. On the 27th of March, 1974, a routine inspection found something that should have stopped everything. A valve on reactor number 5 was leaking cyclohexane, and it had been kept cool by workers spraying it with water. That water, combined with the intense heat of the reactor vessel, had caused a chemical reaction inside the steel wall itself. Stress corrosion cracking. By the following day, the crack in the reactor's side wall had already grown to 2 meters in length. The reactor was immediately shut down and removed from service. Now the plant faced a choice. The correct response, the response that any fully staffed engineering team with a mechanical specialist on hand would almost certainly have pushed for, was a complete review. Inspect all 6 reactors for similar cracking before running any of them at pressure again, and understand the root cause before restarting. The decision that was actually made was different. The priority, explicitly and urgently stated, was to resume production as quickly as possible. A temporary bypass would be installed to connect Reactor 4 directly to Reactor 6, effectively bridging the gap left by removing Reactor 5. Once the bypass was in place, the plant could keep running while the damaged reactor was sent away for inspection. What happened next is where the disaster truly begins, though it will be almost 10 weeks before anyone knew it. The engineers who gathered to design the bypass were chemical engineers, highly qualified and experienced professionals who understood the chemistry of cyclohexane and caprolactam with great depth and confidence. But chemical engineering and mechanical engineering are distinct disciplines, and the distinction matters enormously when you are designing a pressurized pipe assembly carrying tens of tons of superheated flammable liquid. A chemical engineer understands what a substance does. A mechanical engineer understands what that substance does to the structure containing it, and specifically the forces it generates when it moves under pressure around bends and junctions. That second kind of knowledge was the invisible fault line running through everything that followed, and it had walked out of the building with the departed engineer 5 months earlier. The design meeting was held. No mechanical engineer was present. No specialist was called in from outside, though one was known to be available through another division of the company. The emphasis, as the subsequent inquiry would put it, was firmly on prompt restart. The bypass design was sketched out, and because of a specific problem with the layout of the reactors, that design had a complication. The 6 reactors sat on a slope, each one slightly lower than the previous, because the process used gravity to assist the flow of liquid. Reactor 4 and Reactor 6 were not at the same height. A straight pipe could not connect them. The bypass would need to include a bend, a dogleg, to accommodate that difference in level. There was another problem. The correct size of pipe for this application was 28 inches in diameter, to match the connecting flanges of the reactors. But there was no 28-inch pipe available on site. The engineers used what they had, a 20-inch pipe. To connect it to the 28-inch flanges of the reactors on either side, they needed reduction pieces. Each junction point was fitted with bellows, the same type of expansion joint used throughout the plant, designed to absorb movement. The whole assembly was mounted on temporary scaffolding poles. It was not anchored or supported from above. No detailed engineering drawings were produced. The layout of the dogleg was sketched on the workshop floor in chalk. No stress calculations were performed on the assembled structure. The bypass was not pressure tested before it was put into service. What nobody calculated, because nobody on site had the specific mechanical training to think to calculate it, was the effect of the dogleg bend on the bellows. When pressurized liquid flows around a bend, it generates a lateral force. That force, in this configuration, will be transmitted directly into the bellows at either end of the bypass. The bellows were designed to absorb longitudinal movement along the axis of the pipe. They were not designed to withstand a twisting, rotational force applied at an angle. Under normal operating pressure, the bypass assembly was slowly being stressed in a way that its designers had not considered and could not see. The plant restarted. The weeks passed. The bypass held. And because it held, nobody questioned it. Saturday, the 1st of June, 1974, was a warm and sunny day in Lincolnshire. Across the county, people were making the most of the early summer weather. In Scunthorpe, 3 miles from Flixborough, a television crew from the BBC and Yorkshire Television had set up their cameras to cover the Appleby Frodingham Works Gala, a local community event. Nobody there was thinking about the Nypro plant. Nobody anywhere was thinking about it. It was a Saturday. That fact mattered enormously. On a weekday, The Nypro site employed around 550 people. The main office building would be full. Engineers would be moving between departments. Contractors and delivery drivers would be arriving. The walkways between buildings would have people on them. On a Saturday, with a skeleton crew of 72, large sections of the plant were empty. The main offices were deserted. The canteen was closed. It was the quietest it ever got. The plant was in the process of restarting after a brief shutdown. The cyclohexane was already in the system, already heated, already circulating through the bypass under what was called hot recycle, a preparatory phase before full production resumed. The liquid was at operating temperature and pressure. The bypass had been carrying that load, day after day, for nearly 10 weeks. At 8 minutes to 5 in the afternoon, the bypass failed. The exact sequence of what happened in the seconds before the explosion would be debated for decades. What is known is that the bellows gave way. The dogleg assembly, subjected to weeks of twisting force at a level nobody had calculated, buckled. In a matter of seconds, somewhere between 40 and 60 tons of superheated cyclohexane poured out of the ruptured pipe into the open air. At atmospheric pressure and at that temperature, it did not stay liquid. It flash evaporated instantly, expanding into an enormous, invisible cloud of flammable vapor that began spreading rapidly across the plant. The cloud needed an ignition source. The Nypro site had many furnaces, steam systems, electrical equipment, vehicles. The vapor cloud reached one of them, almost certainly a furnace associated with a nearby hydrogen reformer plant, within seconds. What followed was an unconfined vapor cloud explosion, a detonation of a fuel-air mixture in open space, with no walls or containers to limit its force. The yield has been estimated at the equivalent of between 15 and 45 tons of TNT. The entire reactor section of the plant was obliterated. The surrounding structures were destroyed. The shock wave radiated outward. One worker who survived described being thrown full length across the road by the blast, then lying still as debris and liquid rained down from the sky. Another man who had finished his shift hours before heard the explosion from miles away and immediately drove to the station to report for duty. A firefighter 6 months into his career was at home on his day off when he heard the bang and stepped outside to see a vast column of black smoke rising over the Humber. He drove straight to the station. The call that had gone out as a 5-engine response had, by the time the first crews were 4 miles from the site, already escalated to 20 engines. By the time they arrived, the scene resembled, in the words of those who were there, a war zone. The control room was gone. It had been a brick building positioned close to the reactors for operational convenience, standard practice at the time. The building offered no meaningful protection against the overpressure of even a relatively small explosion, and this was not a small explosion. The blast hit it with enormous force. The brick walls collapsed inward. The heavy concrete floor above the room fell. All 18 people inside were killed instantly. No one in the control room escaped. 9 more workers died in other parts of the plant. A delivery driver parked outside died of cardiac arrest. The fires that started in those first seconds burned for 10 days. By the end of that Saturday afternoon, 72 of the 79 houses in Flixborough village had been damaged. In the neighboring village of Amcots, 73 of 77 homes were affected. Nearly 800 buildings in Scunthorpe, 3 miles away, had broken windows or structural damage. Debris from the plant was found 6 kilometers from the site. Smaller pieces were recovered as far as 32 kilometers away on the outskirts of Hull. The blast had been heard in Grimsby and Hull, over 35 miles distant. Around 200 families were made homeless overnight. The BBC and Yorkshire television crew who had been filming the gala in Scunthorpe captured the disaster on film. It was on the evening news that same night. Dave Roberts was 21 years old and 8 months into his training as a plant operator at Nypro. He had been scheduled to work that Saturday, but had taken annual leave to spend the day with his fiancée. Nearly 20 of the men who died were people he worked with every day. One of them was his best friend. In the weeks that followed, he and other surviving workers were brought back to the site to help dig through the rubble alongside mine rescue teams. When a body was found, the workers were sent to a hut for a cup of tea while it was removed. That, he would later say, was the counseling available to them in 1974. The British government moved quickly. Within weeks, the Secretary of State for Employment, Michael Foot, announced a formal court of inquiry into the disaster, to be chaired by a senior barrister named Roger Parker. It was the longest inquiry of its kind ever held in the United Kingdom. 70 days of formal hearings, stretching from September 1974 through to February 1975, with testimony from more than 170 witnesses. The central technical question the inquiry had to answer was a deceptively simple one. Why did the bypass fail? The investigation took apart every element of the assembly. Test rigs were built to replicate the exact configuration of the dogleg pipe and the bellows. Experts in fluid mechanics, in material science, and in structural engineering were brought in to examine the wreckage and model what had happened under operating conditions. The answer that emerged, and that the inquiry ultimately accepted as the most probable explanation, was what became known as the 20-inch hypothesis. The dogleg configuration of the bypass, combined with its reduced pipe diameter and the absence of any rigid upper support, meant that the bellows at the reactor 4 end of the assembly were subjected to a twisting, compressive force every time the system was under pressure. This is called bellows squirm. Over time, under repeated cycles of pressure, the bellows deformed. Eventually, they failed catastrophically, releasing the full contents of the pressurized system in seconds. The force that caused the failure was not exotic or obscure, and that was perhaps the most disturbing finding of all. It was a straightforward principle of mechanical engineering. When pressurized fluid travels around a bend, it generates a lateral force that must be accounted for in the design of any joint or connection at that bend. The inquiry found that the engineering knowledge required to identify this risk existed, was taught in mechanical engineering programs, and was well understood in the profession. It simply was not present in the room on the day the bypass was approved. Nobody had called for outside advice. The man who would have known to raise the question was gone, and the gap his departure left had never been formally acknowledged or addressed. The inquiry also delivered a verdict on the control room that went beyond the physical facts already visible in the wreckage. It was not just that the building had been poorly placed or poorly built, though both were true. The deeper finding was that prior to Flixborough, the risk of an unconfined vapor cloud explosion on this scale had simply not been incorporated into any standard guidance for the design or location of occupied buildings at chemical plants. Nobody had required plant designers to model what would happen to a brick structure under explosive overpressure, because nobody had made it a condition of operating a facility of this type. The control room at Nypro was built the way control rooms everywhere were built, and that was precisely the problem. The inquiry was careful in one important respect. It explicitly declined to attribute criminal blame. Its conclusion was that no one at Nypro had knowingly and deliberately accepted a hazardous course of action in disregard of safety. What it found instead was a systemic failure of judgment at every level, from the decision not to call in a mechanical engineer, to the absence of drawings, to the lack of pressure testing, to the broader culture in which production pressure consistently shaped engineering decisions. The disaster, the report stated, was caused by the introduction into a well-designed and well-constructed plant of a modification that destroyed its integrity. But the inquiry also raised a question it could not fully answer within its own scope, and it is perhaps the most troubling question of all. At the time of the explosion, the processes used to control and approve hazardous chemical plants in the United Kingdom were startlingly weak. Local planning committees, with no technical expertise in industrial chemistry, granted permission for facilities to operate with large inventories of dangerous substances. Once built, those facilities were subject to no ongoing mandatory safety review by any national body. Nobody had mapped how many other plants across Britain were operating with similar vulnerabilities. The honest answer, as several experts noted in the aftermath, was that nobody knew. The aftermath of Flixborough moved through British society in two distinct waves. The first was immediate and emotional. A country shocked by the sight of a modern industrial plant reduced to rubble on a peaceful Saturday afternoon, with lives erased in seconds by something that had been presented as a temporary plumbing modification. The second wave was slower, more institutional, and ultimately more consequential. It reshaped the framework of industrial safety not just in Britain, but across an entire continent. The Health and Safety at Work Act had been moving through Parliament when the explosion occurred. It was passed later that same year, and several of its provisions were directly sharpened by the Flixborough disaster. For the first time in British law, employers at high-hazard facilities were held to a general duty. to reduce risks to workers and to the public as far as was reasonably practicable. The old system of specific prescriptive regulations that covered boilers but not cyclohexane, that applied to steam but not to vapor clouds, was no longer adequate. The new law placed the burden of identifying and managing hazards on the people best placed to understand them, the operators themselves. The Health and Safety Executive was established as the independent national regulator for workplace safety. The Advisory Committee on Major Hazards was set up almost immediately after the disaster, tasked with identifying which types of industrial installations posed the greatest risk and recommending appropriate controls. Between 1976 and 1984, this committee produced 3 landmark reports that defined what it meant to manage a major hazard site responsibly. They introduced the concept of formal hazard assessment, the systematic identification and quantification of risk before anything is built or changed. They required operators to think through not just what might go wrong, but how bad it would be if it did. One of the most direct and lasting changes to emerge from Flixborough was the formalization of what is now called management of change. Before 1974, it was not unusual for modifications to chemical plant, even significant ones, to be approved informally on the basis of operational experience and engineering instinct, without documented review, without formal drawings, and without independent verification. After Flixborough, that approach became unacceptable. Any change to a hazardous process, however temporary, however seemingly minor, had to be reviewed by qualified engineers, documented, assessed for risk, and signed off through a formal procedure. The bypass at Nypro had failed every one of those tests. The new rules made sure that no modification could ever be approved the same way again. The design of control rooms at chemical plants worldwide was reconsidered entirely. Prior to the disaster, these buildings were positioned close to the process for operational convenience and built to ordinary commercial construction standards. After it, guidance was issued requiring that occupied buildings at hazardous sites be sited and constructed to withstand blast overpressure. Blast-resistant control rooms became the standard. The lesson was simple and had cost 18 lives to learn. If you're going to keep people in a building next to a plant that contains enough flammable material to produce an explosion of this magnitude, you have to design that building to protect them. 2 years after Flixborough, a chemical plant in Seveso, Italy, released a toxic cloud of dioxin over a residential area, exposing tens of thousands of people to one of the most dangerous substances known to science. Seveso, coming so soon after Flixborough, made it impossible for European governments to continue treating these incidents as isolated national problems. Together, the two disasters drove the development of the first European directive on major industrial hazards, the Seveso Directive of 1982, which required member states to identify and regulate facilities handling dangerous substances, mandate formal safety reports, and ensure that planning authorities had the information they needed to make decisions about where such plants could be located. That directive has been updated twice since and remains the foundation of industrial safety law across Europe today. The regulatory framework that governs every major chemical plant, refinery, and fuel storage terminal in Europe traces a direct line back to the afternoon of the 1st of June, 1974. In Flixborough Village, a memorial was erected at the rebuilt plant in 1977. It was a bronze sculpture of mallards landing on water, a quiet and local image for a very local grief. When the plant eventually closed, the sculpture was moved to the pond at the parish church. On New Year's Day, 1984, it was stolen. It has never been recovered. What remains is the stone plinth it stood on, with a plaque listing the names of the 28 men who died. The site of the plant itself is now a light industrial estate. The reactor halls, the control room, the scaffolding-mounted bypass, all of it is gone. A power station stands where the cyclohexane reactors once ran. The human cost of the disaster did not end with the last fire being extinguished. Roberts, who had returned to the site in the weeks after the explosion to help dig through the rubble, who had been sent to a hut for a cup of tea each time a body was found, said that it took him the better part of 20 years before he was able to speak about what he had been through. He was not unusual in that. The survivors of Flixborough carried what they had experienced largely in private, in an era before the language of industrial trauma existed in any formal sense, in workplaces where the expectation was simply to return to the job and carry on. What happened to those men in the rubble, and in the years that followed, is a part of the story that the official reports and regulatory frameworks that came after Flixborough were not designed to address. The cyclohexane oxidation process that caused the Flixborough disaster is still in use today in parts of Asia, operated in plant designs that closely resemble the original Nypro configuration. The engineering lessons of 1974 have not been universally applied. The regulatory frameworks that Flixborough helped to create exist only where governments have chosen to enforce them. And the fundamental human tendency that made the disaster possible, the tendency to treat a temporary fix as a permanent solution, to let production pressure crowd out engineering caution, to assume that because something has not yet failed it must be safe, has not been engineered out of the human condition. That is the final and most important thing that Flixborough teaches. It was not caused by ignorance. The people who approved the bypass were qualified engineers. They were intelligent. They were experienced. They were working hard under real financial and operational pressure, trying to keep a struggling plant running in a difficult economic climate, making a decision that, to them in the room on that day, seemed reasonable. The disaster was not the product of malice or stupidity. It was the product of a gap between what the people in the room knew and what the problem actually required. And gaps like that exist in every industry, in every country right now. Flixborough is a reminder that they can close instantly and without warning at 8 minutes to 5 on a Saturday afternoon in June.